Hey everyone, I'm back again with another lecture, our second to last lecture of the semester, so I'm sure that you're all happy about that. This one is lesson 12, chapter 15, and it is on pollution and waste disposal. So we're going to go down a few different rabbit holes during this lecture. I'm going to focus on a few that I work with. This is another area that I work with quite a bit in my field of expertise and my career. But you'll see this is very diverse. So some of these things I really don't work with that much, but some of them I do work with very closely. So as we go through this, what you're going to learn about is the different types of waste that humans produce and inject back into our environment, and how, remember, I always go back to this, that balance in nature. We're affecting that balance, that where the ideal is, we're upsetting that, and how we affect the environment, the atmosphere, the water, the groundwater, and all that. So just, I'm not going to go through this very closely. The history of this, when humanity was evolving socially, once humans started living together and forming communities and living in small towns, you saw a concentration of things. Whereas if humans are living intermittently in the woods, your general area, the waste that you produce might not be that evident. But when you get concentrations of people living together and all that waste is together in one spot, suddenly you realize, hey, we have to do something about this. And usually that was the hard way. Usually by nature, and human nature back then was the same as it is now. They probably ignored it for a very long time until it got to a point where they realized we can't keep doing this. We have to do something about this. And it's not just aesthetically, like you see here. You see a lot of garbage laying around. It's not just that. It's water quality. People started getting sick. Things like that. And here you see, actually, this is an open sewer line down the middle of a settlement here in Kenya. This is where their wastewater goes, and it sits there, and they have to deal with that. So other things you see in history, these photos, air pollution on the left. On the right, I'm not sure exactly what river this is. This has happened in Chicago, and I think in Cleveland as well back in the day. It looks like they're just putting out a fire on this boat, but actually the river's on fire. There were so many chemicals in the rivers in these cities that at times they would catch on fire. The surface of the water had so many chemicals on it that it would burn. It could catch on fire. So that tells you, even as we started to progress with our society and our culture, we still were very lazy and lackadaisical about these things until it became a really big deal. And people start saying, hey, we've got to do something about this. So you can see here that even though this is ancient history to most of you all, this is not that long ago in American history that we started having environmental policy. 1969, NEPA was passed. That's the Environmental Policy Act. The Clean Air Act in 1970, the Clean Water Act in 1972, RCRA in 1976. All of these things are things that I have worked with in my career, and they're still debated today. There are still political factions in the U.S. government that want to get rid of these things because they're pro-business, pro-money, and they think these things don't matter. However, the evidence is very, very clear that since these rules and regulations were brought into effect, our environment has exponentially improved since those days. It was terrible. So we still have these battles going on within our government, unfortunately, because of money. Because some people don't like these rules and regulations because they might not make as much money as they did before. So Superfund. Superfund is an EPA program. It's basically when there was an industry or some type of facility that horribly polluted the environment on that specific site, and it's so polluted that it's now hazardous. So the government has a fund that they have to go in and clean up these sites after the industry leaves. So again, that goes back to kind of the political discussion. Some of our tax dollars have to go clean up after private industry. That's why we have taxes like we do. Because these industries were allowed to just pick up and leave after they finished whatever they were doing, and then it was left for the community, and in this case the federal government, to clean that up. As you can see, the proposed additions to the list has pretty much flatlined since about 1995. That stayed kind of the same. So that means we're doing a little bit better job with our environmental regulations and people causing these Superfund sites. The orange is construction not complete yet. That means they're working on them, but they haven't remediated the site. The yellow, which is kind of hard to see on this screen, that means construction, it's been remediated, but it's not cleared the books yet. All the government protocol that they have to do to get them cleared off. And then the green are ones that have been completely remediated and they're off the list. So as you can see, we've made progress on this over the last 20 to 30 years, but we still have a long way to go with this. The difference between contamination and pollution. So contamination means, so if you do your samples, air samples, water samples, and you have a substance that humans have put there and it's above the natural background concentration, that means that it's contaminated, that we have contaminated that water or air source, whatever. Now, polluted is a step up from that. Polluted means it's at a level that can be dangerous or harmful to humans or the environment. So once it gets to polluted stage, then it gets a little bit more serious. Contaminated means we probably should be working on it to get it remediated, but it's not quite dangerous yet. Polluted is the next step up. So there's two sources of pollution in general, how we categorize these. There's point and non-point source, and this is something I work extensively with, especially on the non-point source side of things. So a point source, and think of this, the way I always kind of think about this is you think about a river. This picture right here is the best example of what a point source is. You have a water body, and you have a point source. This is one point. All this effluent, this water, this whatever this is flowing out of here into this river. So whatever factory or whatever is above this, we can't see in the picture, it's putting out this water. That's a point source. That means we know exactly where this water is coming from, and it's all coming from this one pipe. That's the best example of a point source. Sewage treatment plant is a point source. It's coming from one location, like one pipe. There might be two pipes, but they're the same, right next to each other. So that's a point source. Non-point source means it covers a big geographic or spatial area. Think about farms. Think about the runoff from the parking lots in cities. Even it has a picture here of a person putting fertilizer on their lawn. Those are non-point sources. That means we can't pick one specific point up this riverbank here to say, okay, this is coming from right here. It's coming from all of it, really. So that's what we call a non-point source. So that's the difference in those two. When we have contamination, and this can be in the air or water, either one. It's more visible in water, and it's easier to show an example in water. You have plumes. You can also see contaminant plumes out of smokestacks sometimes. They don't last a long time because they tend to diffuse in the atmosphere very quickly and kind of mix, and they kind of go away visually, but they're there chemically. If you could go up there and monitor areas downwind of that plume, you would find higher concentrations of pollutants. Same with water. And here are ones that are visual. You can actually see these. This is likely a runover event in a wastewater treatment plant is what it looks like to me. I really don't know that, but that's kind of what it would look like if it would happen in one of those. And you can see the plume of pollutants have come out of this structure right here and run up the coastline a little bit. So as you monitor this stuff, as you go away from it, it starts mixing with more and more ambient water, and the concentrations get less as you move away from the plume. And you can see that here. You can see in the middle here, really dense. It's going to be very highly concentrated, and as you move away from it, you're still going to get contamination and pollution, but it might be less dense as it is right in the middle. So that's what we mean by a contaminant plume. And here's an example of that in an aquifer. Again, remember our studies of aquifers. You have a leak. This would be an oil tank or a gasoline tank. It leaks out this fluid. It gets down into this unconfined aquifer. Here's the water table right here. Remember, this could be rock or it could be sediment, so that's going to determine how fast the porosity and permeability of this aquifer is going to determine how fast it moves through and how much it disperses through this aquifer. And eventually, it may end up in a local river. If this is a river that receives water from the aquifer, from the water table, then it could end up in that river. It also can contaminate water wells that are drilled down into this aquifer. Now you can see here, and remember our test question for that unit, I had a question about karst. If you drill down deep enough past the karst, would this water be cleaner? In this case, it would be, because here you have an impermeable layer that's keeping this contamination in this unconfined aquifer. It's not getting down in the confined aquifer, so that makes it a little better. However, with anything, there's always potential to, with human intervention, to go past this. And what I'm talking about is, I'll be very suspect if you have a well drilled down through this impermeable layer. How well did they construct this well? Did they really seal this hole off good enough? If not, it could leak down into this confined aquifer as well if this was not drilled and sealed properly. And again, human nature, I don't trust that a lot sometimes with regards to endeavors like that. So whenever we inject our influence on something like this, there is opportunity for that to be worse instead of better. I'm throwing up the karst aquifer diagram again. Just again, this is our test question. These are some wells drilled down here. Just I wanted you to think about, get a mental picture if that gas tank was just sitting next to this sinkhole right here. In this previous diagram, you know, this plume could move over the course of a year in this aquifer. If it's a very slow moving aquifer, it could move in the measurement of maybe feet per day, very slowly. Whereas in karst, if that gas tank's sitting here by this big sinkhole and runs straight down into here, it could move in miles per day very easily. Just get in that water, in that stream underground, and just take off. In no time, it's to our base river, and you have a whole lot of contamination all through the groundwater and in the base river as well. So just wanted to kind of bring that back up in your memory there. So when we start talking about solid waste, so here is a pie chart of solid waste that humans produce. When we talk about solid waste, that more or less means garbage to us. In layman's terms, that's just the garbage that we produce. We'll get into hazardous waste in just a minute, but solid waste is garbage. And this is a pie chart that kind of shows you what our typical garbage is consisted of. And you can see here, a lot of this, almost all of it really, could be either recycled or composted or something like that. And we could really cut down on the amount of household garbage that we have in this country. We simply don't do that. We're getting better than we were, but we're still nowhere near where we need to be. Food scraps, for instance, that's 15%. That's a lot of just straight biological material that could be put in a compost pile out in your yard. That's that much space that would not go into a landfill and sealed off forever, taking up space in that landfill. Yard trimmings is another one, just like food scraps. Again, these two together with wood as well, you could just compost out in your yard, and that never goes into the garbage pipeline. At our home here, we compost every bit of our food. No food scrap goes into our garbage. It all goes into composting, same as yard trimmings. So little things with each of these topics could make a big difference in how much ends up in our landfills. And landfills are a problem. We've had them for a very long time. It's out of sight, out of mind kind of thing. When you throw something in your garbage at home, do you think about where it ends up, where it goes, or how long it's going to be there? No. Nobody thinks about that. Hopefully you do now after you've taken this course. But this stuff is basically put in a big hole in the ground. Hopefully that is a more modern landfill which has a liner. So hopefully that somewhat contains all the rain and moisture that filters down through this. And of course it's picking up chemicals, it's rotting things, all kinds of stuff is in this garbage. You can imagine what's thrown away in garbage is in every household anywhere. So this has got a lot of stuff in it that can cause problems for the environment. So the way the landfill is supposed to be constructed is supposed to have a big liner to where the leachate, the leachate means all the goop and moisture that settles to the bottom is captured and then hopefully incinerated. And sometimes they use that incineration as a source of energy for communities. However, if you have a hole in that liner, or if it's not installed properly, or there's an issue, which there more oftentimes than not are issues, then you can have this leachate leaving that landfill, getting into the groundwater, and really, really causing problems in local areas. So even having a landfill, even though it's burying stuff and it looks like it's outside on a mine, in today's world, these landfills have to be monitored heavily. They actually produce gases that they vent out, and they capture these gases, methane gas in particular. They vent that out, and then they can use that for some other purpose. But these things have to be run really well to prevent any problems down the road. Even ones that have been closed for years still have these kind of issues, so they still have to monitor those. So again, this is what the beginning of a landfill might look like. These big, huge, heavy liners that will go in. And as they put garbage in these, intermittently they'll put caps on them with typically clay. Sometimes it's just dirt until you get to the very top, and then they'll put a clay cap on top of it. And that clay cap is designed for that. Remember, clay kind of swells and shrinks. If it gets wet, it kind of swells up, and hopefully that water will run off instead of seeping down through here and creating even more leachate. So this is a very, very large endeavor to have a landfill. Now, as you can see, over the years, the number of landfills has decreased. Now, these are active landfills. Remember, all these old landfills, they're still there. I mean, they're not taking any new garbage, but they're still underground, and they still have to be monitored, because at any time, if there's a rupture in that lining, you could have big, big groundwater problems. And probably the older ones are even worse, because there was less recycling back then. There's more potentially hazardous materials back then that we used. So those are probably even worse than the active ones with regards to the potential for problems. And this is in your textbook. I'm not going to talk about this very long. Just the best ways to remediate or process our garbage. This is a pretty useful chart here. Our solid waste trends over the years, as you can see here. You can see the total waste generated is on a steep incline up. Fortunately, recycled and composted has also gone up quite a bit, but it's still nowhere near where it needs to be. But it is better than it was, say, in 1965 or 1970, definitely. We have incineration sometimes with larger cities, and that's in a couple of the videos that I assigned to you in this lesson. And then landfills, there's still a lot of stuff going in landfills, but it's kind of flatlined because these other things are taking up some of the slack for what goes into landfills, but it's still way, way too high. Recycling, this is a topic that is very complex, and it's something that, a couple of angles here. First of all, if you just look at this chart, you can see these are percentages of different types of things that are recycled. So we do a decent job, and like it says here, lead batteries I'll agree with, corrugated boxes, I'm not sure if that's accurate or not. It's definitely not in Kentucky. I don't know that many people that actually recycle their boxes. Apparently some people do somewhere. And then you have different types of contaminants down here, or garbage. And you can see down here plastic is the least. And there's a few reasons for that. First of all, plastic was, when it's initially made, or traditionally anyway, it was not made to be recycled. So the recycling process is pretty detailed as far as technology. Another thing is economics. So this is something that I've mentioned over the last few lessons, I've gotten more and more into kind of politics and economics, even though that's not science. As scientists, we have to think about that. And the reason we have to think about that is because, so let's say I'm a scientist and I come up with an idea on a better way to recycle plastics. It's more efficient. Great. We're going to do this. Great idea. So historically, a scientist, that's what they do. They create this technology, these ideas, and that's what they do, and that's the end of their job. Well, now, as we've evolved, scientists have started to realize, you know what? I can come up with the best idea in the world, but if somebody's not making money off of it, it's not going to get done. And that's just the bottom line of human behavior. It's got to be profitable somewhere for somebody to want to do it. It doesn't matter how good it is for the environment or human health or anything like that. It comes down to money. So as a scientist, if I invented something like that, my next step would be, okay, how can we have this new technology, so how can I make this profitable? How can I sell this to the people with all the money and the ability to build these things? How can I sell this to them so that they're going to make money, so they're going to actually do it? So scientists have had to learn a lot about economics as well, because in today's world, again, money rules the show. I mean, that's what drives everything. So now we're going to jump to solid hazardous waste. So hazardous waste is a type of waste that obviously it's pretty self-explanatory. It's more hazardous. It's more acute in the way it affects human health and the environment. So normal garbage, like your papers, even your plastics, I'm on the borderline where if it's hazardous or not. I think it's hazardous over time, over geologic time. In the short term, a plastic bottle is not going to hurt you as far as we know yet. So I would not consider that hazardous, but hazardous is more acute. So a plastic bottle right now is not going to hurt you. But if you were to drink water that had arsenic in it, that's hazardous, and it's going to hurt you like right now, right away. So hazardous waste is a classification of waste that means it's acute and it's immediately dangerous to life, either in the environment or to people. So a lot of sources of hazardous waste are going to be your electronic waste, your batteries, scrap tires, and you can see photographs of these here. Chemicals from either cleaning chemicals in the home that we use to clean with. Bleach would be a hazardous waste. And then you have industrial chemicals from factories and plants that are going to be hazardous waste. So when we have hazardous waste, there's the solid hazardous waste, which is going to be your batteries, your electronics, and all that. Then you have liquid hazardous waste. And that's going to be those cleaners that I mentioned, or stuff from factories. Like if you have some kind of leachate from a factory, or an acid that they use in a process at a factory, those are going to be liquid hazardous waste. And they're going to have to be dealt with differently than other types of liquid waste. So either in a secured landfill, which is rare, you would have some way to kind of solidify that stuff or neutralize it before you put it into the landfill. You can incinerate it. Again, you're transforming the chemicals from a hazardous substance to potentially non-hazardous substances, or at least substances that you can cut down the volume and collect in a solid capacity. That's how some of this incineration works. Or deep oil injection. Now, deep oil injection is when we go so deep in the earth to an aquifer that's confined, that's never going to reach the surface, or hypothetically no other aquifers above it, and that's very hypothetical, that we're never going to use, like a saline aquifer down here. Maybe this is salt water way down deep. As far as we're concerned right now, we're never going to use this. It's confined, so let's just put our stuff down there, our waste. So, again, that term I used, out of sight, out of mind. Is this a good idea? Well, probably in my lifetime, and probably even in your lifetime, it's probably not going to be a big deal most of the time. At some point in the future, it could be. You have a couple of potential hiccups in this. It's going to be out of sight, out of mind for maybe thousands of years, if everything works out all right. But remember, Maybe we don't know everything about this aquifer. Maybe it's leaking up through this impermeable layer and getting into other aquifers above it. Or again, what I went back to in that first diagram of wells, what if when they drill these wells, they don't seal them up good enough between these layers, and this stuff starts leaking back up around this pipe casing into these other aquifers? Well, if there's an earthquake in this area, and it cracks all these rocks around these drill holes. These are all things that we have to consider when we're doing this type of behavior. Hazardous waste roundups, these are some community kind of things that we do. Warren County in Bowling Green, where Bowling Green's located, actually had one about a month ago. I took a bunch of stuff from my household to that. A lot of e-scrap, which is electronics. You see here paint cans, cleaning materials from the home that you no longer need. This is a good way to dispose of these things and not just throw them in your garbage. Have an area in your home you can keep these throughout the year, and when your county or community has one of these, take them and they can dispose of these properly. Now, we're going to go into another waste stream that we have, and that's actual human waste. So this is the big problem. It's a problem that a lot of people really don't want to talk about or might be uncomfortable talking about. But this is a big, big waste producer when you've got so many humans on this planet, and especially concentrated into areas like we have in cities. So in the country, where some of us live, I live out in the country. I don't live in Bowling Green or in Glasgow or any of the small towns. I live way out in the country near Barren River Lake. So we don't have a sewer system out here in the country, so all the homes in the country are on what we call a septic system. So this is kind of a single home waste disposal or sewage treatment setup. I wouldn't call it a sewage treatment plant necessarily. It's a sewage treatment system. And basically what you have, I'm just going to define this very, very basically, is you have a big concrete tank buried in your yard. And all the sewage that is produced, everything that goes down the toilet or down the sink drain, goes through a pipe and into this big tank. And this big tank has a lot of bacteria in it. It's anaerobic, which means it does not have any oxygen flowing into it. There's bacteria that live at the bottom of this that break down the organic waste material. So if you're putting a lot of chemicals in there, if you clean your sink with bleach every day, and you're on a septic system, you are harming that septic system and its ability to clean itself out. So what you have is the solids settle at the bottom. You have clarified water, and that water runs out into other pipes, and you probably didn't see when they built your home, but under the ground there's big like ditches of gravel, and these pipes have holes in them, and slowly that water is allowed to leach out into this gravel and eventually filters through the gravel and then through the soil, and as that filtration happens, that cleans the water. It gets rid of a lot of the harmful bacteria and probably not so much chemicals. The chemicals might be bound up in the soil and not reach the water table, but more often than not they do reach the water table. But that's basically how a septic system works. So as you can imagine, in a karst area, you have one problem up in any of this right here, and you get an open drain, it's going right into a cave. So septic systems in karst areas are not always a great idea. I actually have mine checked pretty regularly. Some people will bury these and never even think about them again. Most people will do that. So the tank itself should be cleaned out or pumped out every probably 5 to 8 years, depending on how many people are in the home. That's hardly ever done either. If you live in a home and you've been there for 20 years and you never pumped out your septic tank, it's probably leaking into the groundwater, because if not, it would be backed up or something by now. So that's basically what a septic tank is. Now, when you have a sewage line, like in a city like Bowling Green or wherever you are in the state, E-Town, Owensboro, or Paducah, or Louisville, you have actually a line that takes that sewage to a wastewater treatment plant. And through that, I'm not going to go through this in detail because I don't want this to go really, really long on this lecture. This is in your textbook. But basically, it filters the water through a system of filters, and then it drops out solids. It recirculates the water. There's a lot of aeration and bacteria, aerobic filtration, and then you have a few chemicals added at the end, and they can let it settle through a filter and then eventually back out to a water source. That might be a river, a lake, the groundwater, something like that. By the time it comes out the back end, they have to do rigorous testing throughout this process, and it has to meet EPA standards before it can be reintroduced into a water body. So it has to be pretty clean to get back into that water source. So that's basically how a sewage treatment plant works. This is a picture of one. That's a pretty large one. Bowling Greens would be probably half of this size that you're seeing here. I can't even see all of this, but what you're seeing here, Bowling Green's probably about half that size. So sometimes you'll have a sewage system that's local. If you have a community out in the country, these are actually really rare. You don't see these a lot, but sometimes you'll see a very small-scale sewage treatment plant. So agriculture and urban activity. So you see these put together, and they're actually polar opposites, but they're both non-point source pollution. Remember that term, non-point source. So you have a lot of, in agriculture, you have chemicals like fertilizer and pesticides, you have animal waste, and you have sediment pollution, erosion, that's increased because of agricultural activity. This is a picture of a feedlot. This is a picture of a feedlot, which a feedlot is where cows are brought in. They are fed. You can see it's not a pasture, so they're not eating grass. The feed is brought into them. They gain a bunch of weight, and then they're sold and processed for beef. So this is a picture one. This would be out in the Midwest somewhere. Think Kansas, Nebraska, somewhere out there, because it's so flat. This is obviously extensively huge area, and these things are a huge contributor to water pollution, both groundwater and surface water, because you can see there's no vegetation, there's no filtration. When it rains, it simply runs off these places, and that stuff enters the groundwater and or surface water. So beef production in this country is a huge contributor to both climate change and to our ambient pollution that we have in our waterways. So I actually work with this a lot. However, I'll work on it in Kentucky. Ours are smaller in scale than what you see out in the Midwest. These would be pictures of feedlots that I have actually worked on with the producers, trying to get them to do better than they are. You can see no vegetation at all here. You can see the tracks. There's too many animals on this land. It's not, remember that word sustainable that we used earlier in the semester? It's not sustainable to have that many animals on this much land. Now here you don't see a lot of cows, but they're there. Trust me, they're just not in this picture. You can see the field next to this doesn't look quite as bad as this one, but this is way overgrazed, and you can see the results. Not only does this produce a lot of pollution to get into groundwater and surface water, but it also is very unhealthy for these animals. So this leads to the quality of the beef that you might eat, or even how much money this farmer makes. If a farmer has cows standing in this junk all day, his cows are not going to be healthy, and you're going to see high mortality in those animals. This is a picture. I just wanted to put this up. This is a typical pasture land setting. This is what you would like for it to look like where beef is raised, where they can graze. There's enough forage for them to sustain themselves on. You don't have to bring in a lot of feed outside of the winter months. That's what you want to see where you have cattle, not this. So here, I wanted to bring this up because I told you I worked on these here in Kentucky. I went to Google Maps just before I did this presentation, and I found one of the feedlots that is pretty local to Bowling Green. This is actually in Monroe County, Kentucky. So this is just a screenshot I took of Google Earth. You can see, again, this is southern Kentucky. You can see a big river flowing through here. It's kind of muddy, so this is after a big precipitation event. This looks like it's kind of springtime because you have green fields, but the tree areas are not as green yet, meaning the leaves have just started coming out. But then if you look closely, right in the middle of the screen, you have all this green and trees, but then you have this big area of dirt. So you think, okay, well, what's that? Well, I'm going to zoom in a little closer, And this is that area of dirt. And that really shouldn't look like that, because you see all the other fields are green. And again, here are the trees that all the leaves haven't come out on them yet. So these are all trees, but then there's dirt. And you have a big river flowing right around this. So it's right on a river. So that can't be good, right? So now I've zoomed in all the way and kind of taken an angle on this. This is that area. You can see the river is right here, running muddy. And you can see individual cows on this land. This is a feedlot in Kentucky. Again, it's not the scale of the ones you see out in the Midwest, but you can see the environmental degradation here. There's just too many animals on this land for the land to support those animals. The density of the animals is too great, therefore vegetation will not grow because it's repeatedly crushed, stomped down, eaten. You see the veins here where the mud is washing off into this gully. It eventually is going to run down here to the river. That's part of the river. The reason the river is so muddy is because of stuff like this. You're also getting a lot of biological organic contamination into the water. The fecal chloroform from the animal waste gets into the water. So you can see that's not good. That's not a good thing. Luckily, there is some tree growth around the river, so at least they're keeping them right off the edge of the river. But still, this stuff is running into these gullies and running right into the river. So this is a really wide version of this, and the reason I wanted to do that is because I wanted to show you where this was. So this place mark right here is where we were just looking. So this is right here. This is the river that surrounded it. Flows down here into this big water body that is known as Bering River Reservoir. Cemetery Road is right here, so Bowling Green is going to be right up in this area. So you might have heard, we mentioned this in a previous lesson on water resources, the harmful algal blooms in lakes. Do you think Bering River Reservoir gets any harmful algal blooms? Of course it does. It's had several in the past few years, and it's from operations just like this. So these are the types of things that I work on in my career, and I work closely with farmers to try to prevent this type of thing from happening on our water bodies. Atrazine is a chemical that is put, it's a pesticide, they put it on corn crops typically. You can see here where the atrazine is most widely applied. Kentucky has a good part of that out in western Kentucky. The Mississippi Basin is here, of course, so you have a lot of atrazine flowing into the Mississippi River. This is a good diagram showing you, this is 1991 and 92, when you see the atrazine spikes. So this is the concentration, and this is where you see it. Of course, we don't farm typically in January, February, March. You see a little spike in the beginning of April, and then May it goes crazy. That's because they're putting it on the crops then, and it's pretty much survives through the summertime until the end of August when we harvest the crops and we no longer have it on there. So that's just a diagram that we use as scientists to see, okay, when is this pollution occurring? So atrazine's pretty normal. I mean, we can predict that pretty well because it's a crop. The animal waste, on the other hand, is throughout the year. And this gets us into what we call the Mississippi River Dead Zone or the Gulf Hypoxia Zone. Again, going back to our previous lesson, this is the Mississippi River Basin. All this area flows down the Mississippi eventually to New Orleans. And along the coast of New Orleans, where you have the Mississippi flowing in, there's a zone in the Gulf, and you can see where the water mixes right here. This is from sediment from the Mississippi River. This is the ocean. This is actually out in the ocean. That's an oil platform back there. I've seen this in person in a boat. I've been out and seen this. It's very definite where that line is. And everything on this side, if a fish is over here, it's going to die. Any marine life's going to die. There's no oxygen in the water here, whereas over here it's normal. So this is a very big effect. And think about it like this. You know, we want to support our farmers and everything, but the pollution from the farms is going down here, and it's putting other people like fishermen out of business. So we have to work together on this. I'm not saying get rid of farming. I'm saying we need to adopt practices in farming that are going to be more sustainable so that we can work together and alleviate these problems and pressures on other groups of people. So I actually work with a task force called called the Gulf Hypoxia Task Force. I was actually in Wisconsin back in June of this year. We had a meeting up there. I'm not actually on the task force itself, but I work closely. I'm with a group that works closely with them. And we did a training up in Wisconsin on some of these best management practices that we help install here in Kentucky. And each state in that whole watershed, so that's several states there, 25 or 30 states, have a part in this task force. There are some core members that are along the main stem of the Mississippi, and we try to work together on these things. And this is the website, if you curious, want to look it up, for that Gulf Hypoxia Task Force EPA website. In Kentucky, the way that we're trying to address our issues that contribute to this website right here is where you find that. This is a DOW website. I assisted Division of Water, that's DOW, with the development of this nutrient reduction strategy. We shared a lot of data on this and helped develop this reduction strategy. You can go to this website and read all about it. It's actually pretty interesting what we look at. The thing is, though, what we have to remember is it's all voluntary. We have a lot of EPA regulations. Farmers are exempt from most of them. So what I do in my programs is we actually pay farmers to implement these practices to help reduce water pollution. They don't have to do it. There's nothing mandating them to have to do it. We have some very productive, forward-thinking farmers out there that want to participate in these things and will do it. And then we have the old-school farmers that never want to change anything, and they're still contributing to these problems. So it's a dance that we have to do. In my area, since agriculture is exempt from most every environmental regulation, we have to do a dance to try to get these farmers to do the right thing. The best thing, though, and one of the things that I focus on in my job is almost in every instance, what's better for the environment also is more profitable for the farmer. They actually end up making more money by putting these practices in. And that's my biggest job that I have to do with my programs, is educate them on that money-making thing. If we can convince them of that, then they will join these programs. And it is very true. When you look at best management practices, their animals are always healthier. They sell for more money. They're more productive. They have less mortality. It all goes together. So now we're going to get into something that I don't work with, and that's radioactive decay. Again, I'm not going to go through this in detail. This is in your textbook, but this kind of goes over the nuclear energy sector and how this stuff decays, how it breaks down. They touch on radon here, or this is actually radiation exposure, and this can be different things. Some works, some health, like x-rays and MRIs and stuff like that. And we have something called radon. Radon is a common radioactive isotope that's found in the homes, even here in western Kentucky, from the bedrock. It's nothing that humans have done, but we have to kind of keep it in mind if we live in a high radon area. I know when I worked at Mammoth Cave National Park, they kept up with our time in the cave because we were exposed to a little bit higher levels. Again, it's not very much, and over a lifetime, we don't get enough exposure typically to even make a difference, but it is something that we need to keep in mind. The radioactive waste disposal, this goes back to the last chapter, in that nuclear energy could be a very good form of energy, almost limitless in supply. It's able to produce a lot of energy really fast. However, we do have the disposal issues with that spent radiation. When it gets to a point it's no longer economical, the material gets to a low enough isotope that it's not producing as much energy, we dispose of that and bring in new material, and we have to dispose of that somewhere safely. And I have a good video on that in our lesson for this particular lesson. Atmospheric pollution, acid rain, mercury fallout, and then the radon gas that I just mentioned. So the mercury fallout and acid rain both really have gotten a lot better in recent years. When I was young, when I was in college, acid rain was a big deal. The mercury was too. It didn't get the attention that acid rain did because a lot of the forests in the northeastern United States were dying because of acid rain. You can see here on this map that the air quality is relatively good out here, but when you get over here, it gets less. So why do you think that might be? The answer is because a lot more people live in this part of the country than live out in this part of the country. Once you leave the coast, the Pacific coast, relatively small population here. So there's not a lot of power plants, burning coal and all that stuff. So it's not as bad out here. But once you get to the Mississippi River and east, you got a lot more power plants. And as you go east, that's downwind all these power plants. So as you go in this direction toward the east, not only do you have more people, you have more power plants, and you're downwind, suddenly you have a high concentration of pollutants up in the northeastern part of the United States. So acid rain, again, this used to be a big deal. This is a map comparing 1985 to 2017. As you can see, through regulation, and again, that goes back to those regulations and the people that want to fight those regulations even today, politically, the regulations made a tremendous difference in this acid rain. You can see the comparison between the two maps. It's really not even comparative. The rate of it has gone down so much since those regulations were put into place. Now, you might think, well, the regulations were done in 1970, in the 1970 time range there, 1970, 72, and then you don't see a big difference until 2000s. It takes time. It takes time to close those coal plants down. It takes time to retrofit those coal plants with scrubbers to take those chemicals out of the airway so that it doesn't reach the atmosphere. And it just takes time for you to see the results of this. That's like in my area of my career. We put these practices on the ground across the state. It's going to be 2 or 3 years before we see real-world results in the water quality testing because it just takes time for that to remediate itself. So here I just mentioned a scrubber on a smokestack. Basically what you have is you have your combustion. It goes to a smokestack, but on the way out of that smokestack, it filters through some what we call slurry or powdered limestone, and that mixing with that limestone's very basic. The sulfates are very acidic, so they balance each other out, they neutralize each other, and they fall out down here in the solid waste. So it takes those properties that make the rain acidic out of that discharge, out of that smokestack. Mercury is a heavy metal, very toxic to human life and life in general, and that is also a byproduct of burning coal. Now, I'm not going to go into a lot of detail on that. It's covered in your textbook. But you can see, again, since those environmental regulations took place, and as we instituted them more and more over time, the amount of mercury emissions has gone down drastically since 1990. So, regardless of what people want to say in the political realm, regulations work, and money talks. You have to make it economical. This is the radon gas I was talking about. I'm not going to spend much time on this. Basically, it can filter up through the bedrock. This is a naturally occurring thing. When we disturb the ground, we can exacerbate that and allow a little more easily to get into our homes and stuff. But it is a natural occurrence. We just have to realize where we are in the United States. There are maps on where radon is the most dense in the crust of the earth. And you can look at that and tell if it's something that you should be concerned about. If you don't hear about it here, you probably shouldn't be concerned about it. So that's it for this lesson. Again, we got one more left. I'm sure y'all are stoked about that. And as always, if you need anything, just let me know. Thank you.